All right, y'all, we are going to go through the notes on inverse, and then you can move on to some practice on your own. But quick refresher on an inverse definition. The fundamental definition of an inverse is it means to switch the x and y values. So fundamentally, it means to switch the x and y values. That can look differently on a table, a graph, and an equation, which is what we'll see in a minute. So fundamentally, our definition is switch x and y. The next question is inverse the same as opposite? Why or why not? The answer here is no, because inverse means switching x and y. While opposite means switching signs. So like positive, negative. So for example, here is an inverse. Inverse here would be if I had x and then y, say it was 4 and then 12. The inverse of that point would be they switch sides. So it becomes 12 and then 4. The x value becomes 12, the y value becomes 4. Opposite, on the other hand, would be if those switched signs. So if I had positive 4 and positive 12, the opposite of that would be negative 4, negative 12. So inverse means switching x and y. Opposite means switching the sign. It's kind of a fundamental difference there, and it's easy to get those two confused. Okay? So then, another thing for inverse, almost forgot this, the notation for inverse is f to the negative 1 of x. Okay? That is the notation. That means inverse. If that notation confuses you, you're welcome to cross through it and write the word inverse every time you see it. It's just mathematical notation because mathematicians are lazy and like symbols better than they like words. Okay? So we're going to see how inverses can show up in 3 different representations. The first one here is a table that is wrong. Good. I've already printed all of these. Okay, so let's make it a correct example. This is my x value and this is my y value. Then they should switch between the two tables. So this table should be 4, negative 2, 6, negative 1, negative 7, 0, 1 and 1 will stay the same, and then 8, 2. That should be the inverse. They should switch those x and y values. Lovely. Miss Avery, a typo that I'm catching as I'm doing this for the first time. Okay? So again, inverse in a table just means switching the x and y values. If this notation confuses you, cross through it and call it inverse. Okay. Now we have to generate our own table here. So I'm going to do x value, y value, draw my 4. My x values I'm going to label in blue on my original function. In my inverse, my x values become my y values. And my y values become my x values. Okay. So again, inverse just means switching those x and y values. That one was actually correct. Way to go, Miss Abra. Okay. Next one is graphically. The way that, or the definition for the graph of an inverse is it is reflected across the line y equals x. The line y equals x is this diagonal line here. So whenever I see a graph, I always draw in that diagonal line. And as you can see, this function flips across that diagonal line. It is reflected across that diagonal line. My hands were in the way, you couldn't see what I was doing. Okay, so this function reflects across that blue line. Now, sometimes that can be hard to see or can be confusing. So what I always do is I try to pick a test point if I think they are inverses. Okay, so the test point that I'm going to pick here, I'm going to pick 2, 4. I think that's 2, 4, yep. This is the test point 2, 4. Okay, so if 2, 4 is on my function, then on my inverse function, there has to be the point 4, 2, right? Because they have to switch. So then I go over here and I go 4 up 1, 2. That point does lie on my function, so I know that these are inverses of each other. Okay. So test points are another way that you can kind of double check yourself if the reflection line doesn't make as much sense. All right, now on this U try, it says, are the functions inverses or not? Justify. Okay, so we know that inverses have to reflect across the line y equals x. So I'm going to start by drawing in that line here. Okay, if I took this top function and I reflected it across that line, I should get a function that looks something like this. Okay, and that is not what I see in my original graph. The original graph, I've got this one. Okay, that was my original graph, and let me get one more color. Y'all know me, I color code everything. This light blue function should reflect, if they are inverses, should reflect onto that pink one because it's flipping across the line y equals x. Okay, it does not flip across the orange one. The answer here is no, they are not inverses because the function reflects across the x-axis, not the line y equals x. Okay, so they are not inverses because the function reflects across the x-axis, not the line y equals x. And finally, we are going to look at our equation examples. Again, fundamentally, the definition of inverse is switch the x and y values. With equations, we have to go one step farther and solve for y. So I'm given this equation here, and it's telling me to find the inverse. The first thing I'm going to do is switch my x and y values. That's going to give me x is equal to 1/2. Got to get the color coding right. Y minus 3. So I switched my x and y values. Next thing I need to do is solve for y, or get y by itself. Okay. So to get y by itself, I'm going to draw a little line down my equal sign. I'm going to use my reverse order of operations, or SADMAP. SADMAP. So I start with addition or subtraction first. I see that this 3, there's subtraction here. So the first thing I'm going to do is add 3 on both sides. It's going to give me x plus 3 is equal to 1/2 y. Now y isn't totally by itself yet. Next thing I need to check for is division and multiplication, which I see here with this 1/2. Canceling out this 1/2 can be kind of tricky, but I always think of fractions as division. So if this is divided by 2, then I know to cancel out a divided by 2, I can multiply by 2. So if I multiply by 2 on this side of the equation, I also have to multiply by 2 on the other side of the equation. 1/2 times 2 will cancel out. And then here, when I've got a number on the outside of parentheses, I need to distribute into the parentheses. So this becomes 2x plus 6 is equal to y. And now y is totally by itself. I know that that is my inverse. So I always write it in the correct notation of 2x plus 6 equals negative, or f to the negative 1 of x. Remember, this notation again just means inverse. So that tells me that this equation is the inverse of the function I was given. So that would be my final answer. Alrighty, very, very last one. Find the inverse of 2y plus 3x equals 10. Again, with inverse, my first step is to always, always, always switch those x and y values. This time, they just happen to be on the same side of the equation. So this becomes 2x plus 3y equals 10. So this one looks a little bit different because x and y are on the same side of the equation. But again, do not forget that you always have to switch x and y when you see the word inverse. And from here, we're just going to solve for y or get y by itself. So I'm going to look SADMEP again. And I'm going to look for any addition and subtraction first. I see addition here. So I'm going to cancel that out with subtraction of 2x. That leaves me 3y is equal to, that's a y, not an x, 10 minus 2x. Y is not totally by itself yet. I need to look for division and multiplication next, which I see, because if 3 is right in front of y, that means multiplication. To cancel out multiplication, I divide. If I divide this entire side by 3, I also have to divide this entire side by 3. So the 3's cancel out here, and I'm left with y is equal to 10 minus 2x over 3. That is a totally correct answer. Okay, this is 100% a correct answer. But we also could simplify this if we wanted to by splitting that fraction into 2. So this would become 10 over 3 minus 2 over 3x. Okay? So same thing, this correct answer is equal to this correct answer. They are both correct. We just need to recognize that they're equivalent even if they are simplified. And that is it for the notes. From here, you can move on to the practice worksheet.